All right, so now let's go into how we can come up with an impedance model for this overhead. And what we're going to focus on first is the calculation of the line inductance. And basically, if you have a current that's going through a wire, then that's going to create a magnetic field. And what you're going to have associated with that is you're going to have a like a line inductance that's going to be associated with that magnetic energy storage. And so basically, what we're going to want is we're going to want to get some relationship between the voltage drop across and the current going through. And that's given by Faraday's law. Basically, what you're going to have is you're going to have E is equal to d lambda dt. And so that could be a net voltage, or sometimes we're going to be calculating like a voltage per unit length. You'll see in just a little bit how we're going to set that up. If we have a linear circuit, then we're going to have a relationship between this flux linkage and current, where the ratio of flux linkage to current is going to be an inductance, which has units of henries. And if it's linear, then what we can, instead of worrying about, flux linkage, we can just simply write this relationship between voltage and current in terms of this inductance L, where E is equal to L di dt, right? So this is really what we're after, is we're after expression for this inductance. We may actually express that in terms of reactance, where that's going to be omega times L, depending on if we're working in terms of steady state or if we want to do like transit calculations. And what I'm going to have posted up on the Moodle site is I've got some notes on overhead feeder modeling, and due to the time constraints, I'm not going to go through all this in detail from scratch. I'm going to kind of jump around a little bit and kind of show some of the key results. But if you want to see how all this stuff is developed from scratch, if you haven't seen this before, take a look at the notes I've got posted up on the Moodle site, which actually walks through this from scratch. You're just going to be responsible for the end equations for coming up with the models, not for all the different theory. And it would probably take me like a couple lectures just to go through all the theory. So anyway, I'm just going to kind of show some key results from the notes. So again, we're mostly interested in what's going to happen in steady state if we're working at a fundamental frequency like 50 or 60 hertz. And so if we talk about something like V is equal to L di dt, then if we're going to translate this into say like phasor analysis, then we're going to have a phasor voltage is going to be equal to J omega Li, where voltage and current are going to be phasor values. And so again, we're mostly going to get this set up for doing phasor analysis, and then we're actually going to be going after what's going to be this omega L term directly. Now, if this is a single wire system, let's suppose we just have a single wire. Then if we run a current through here, we're simply going to have what's referred to as a self-inductance L, right? And we don't have to put any subscripts on there because we just simply have the one inductance. But a lot of times we're going to be working on multi-conductor systems. We're going to have like a phase A, B, and C, and also a neutral wire, right? So let's suppose we have two conductors and we've got a current I1 and we've got a current I2. Well, I1 and I2 are not necessarily the same. And what's going to happen in this case, if I'm talking about getting a voltage across this first conductor in terms of a voltage drop, and you'll note I don't always put the tilde above the variable to denote it's a phasor. The fact is a capital letter means it's a phasor. You've got to take into account both I1 and I2 as far as calculating this drop across conductor number one. And so the way we do something like that is through what we refer to as self-inductances. So the first subscript is the voltage, what voltage is impacting. The second term is the current, where we want to utilize. And what we basically have is we have what we call a self inductance. This is going to be L1 one term. Then also what's going to factor into the voltage drop across wire 1 is a current going through I2 through what we refer to as a mutual inductance. And so when we talk about these multi-conductor sort of systems, it's not just going to be a function of I1, but it's going to be a function of the other currents flowing in the other wires as well. And this is going to relate to these mutual inductances, or sometimes what we refer to as mutual coupling types of terms. And that's really what we need to focus on in here is, how do we calculate these two different types of inductances? So again, the notes is going to have more details on this, but basically the way you would kind of do the derivation of these different types of inductances, you assume that you have a conductor that's going to have a radius given by R1. And you have a current I going through it. And what happens is, according to the right-hand rule, that you're going to set up a magnetic field where if you apply the right-hand rule, my thumb's in the direction of current, then basically what's going to happen is the fingers is going to be the direction of the magnetic field. And so we're going to set up a flux that's going to be shown here in the clockwise direction if current's going into the slide page. We're also going to be interested in calculating the net flux out in free space. And for doing that, what we're going to do is we're going to be concerned with, well, what's going to be this flux flowing within an area that's defined by distance D1 and D2 from the center of this particular conductor right here. And then also too, we're going to be doing a lot of these calculations on a unit length basis. And so we have to know, like what the length of this is going to be as well. So anyway, again, if I inject a current through a conductor and I generate a magnetic field where there's going to be a net amount of flux I can associate it with this, then that's going to result in an inductance that's associated with this particular wire. There's going to be two different types of inductance in this case. There's going to be inductance associated with the flux inside the conductor. There's going to be another term associated with the flux flowing outside. And so we can talk about an internal flux linkage, and won't get into the details of this, but it turns out that if you would integrate this expression for the flux as a function of position from the very center of the wire, if you integrate this from 0 to R1, then you're going to get a total flux linkage that's given by mu naught times the current divided by 8 pi. If you divide through by the current, you get the inductance, and this internal inductance is mu naught divided by 8 pi. Mu naught is what we call the permeability of free space. And mu naught is 4 pi times 10 to the minus 7th. You might be wondering, well, gosh, if I'm calculating this total flux linkage within the conductor, why do I use permeability of free space? Well, it's because if you have aluminum or copper, or you have one of these non-ferromagnetic materials, these non-ferromagnetic materials basically have the same permeability as free space. And so the relative permeability for the metal is actually 1, which is why we can use the permeability of free space in this case. All right. So basically, aluminum, as far as conducting magnetic fields, is the same as air. If you we're going to substitute in for the permeability of free space, what you end up with is you end up with a term for the inductance on a per unit length basis. And in this case, this is in terms of meters, where this internal inductance is 1/2 times 10 to the minus 7th henries per meter. All right, so that's one inductance term, is due to the flux actually flowing within the conductor. There's also flux flowing externally to the conductor. And so when we talk about the net flux linkages, which is lambda, we can actually get that on a contour between D1 and D2. And so if we were going to integrate this expression for the magnetic field intensity, what we can do is we can do this integration. And what we find out in this case is that this internal flux linkage between D1 and D2 is going to be mu naught times I divided by 2 pi times the natural log of D2 over D1. And you're going to see this natural log expression a lot. And the thing I want to point out is that when you have a natural log type of relationship, if I were to double the term within the argument, it does not double the natural log of that. And so just the fact that we change the spacings doesn't mean that this is going to change proportionally. It changes according to the natural log. And so if you divide this by the current, you get an expression for the inductance associated with this defining path. This is mu naught divided by 2 pi times the natural log of d2 over d1. And this is going to have units of henries per meter as well. So we can also substitute in for the permeability free space, and then we get this expression for this inductance of 2 times 10 to the minus 7th times the natural log of d2 over d1, and that's in terms of henries per meter. Now, where this gets kind of complex, and this is where you have to kind of go to the notes, is if I have a multi-conductor system that my total flux linkage associated with conductor number 1 is going to depend on I1, I2, and also IN if I have like an N-conductor system. And normally the way this gets done is we choose a reference point for doing this calculation that's way out, far away from our conductors. And so with respect to this reference point, you have a total flux linkage, which is 2 times 10 to the minus 7th. You have kind of like a self-inductance term, if you want to think about it that way, which is natural log of 1 over this term we'll call the GMR. You'll have a second type of term that's due to the other currents flowing through the other conductors. And this is going to relate to flux linkage 1 by the distance between the second conductor where you have the current I2 flowing and the first conductor. And so depending on those relative distances between the conductors, that's going to kind of come into play for this net flux linkage expression. And this GMR term turns out to be, for a solid conductor, the actual radius times e to the minus 1/4 power. Okay, so it's like a modified radius in a way. I want to point out this is for a solid conductor. If I actually have a conductor made out of individual strands of wire, then I've actually got to get this number from the manufacturer because there's airspace in here. And this kind of relates to the airspace as well. And so if there's little gaps between these individual strands, you've actually got to go to a table from the vendor of the wire to get this GMR number. So if it's solid, this is a term to use, but if it's not solid, then you have to get that number from a table. Now, if we have sinusoidal currents and we're working in the phasor domain, then our phasor voltage across conductor 1 is going to be J omega times this phasor term for the net fluxes. And if I break this out, then what I'm going to have in the phasor domain is going to be J omega times 2 times 10 to the minus 7. So this is basically the inductances type terms, right? Where this first term for I1 is going to have the natural log of 1 over GMR for conductor 1. And then these other terms are going to have expressions that are going to be natural logs of 1 over the distance. And this is going to have units of volts per meter. So the takeaway from this is what I can do is if I want the voltage just across conductor number 1, I can write that in terms of all the different currents in my N conductor system. I'm not really saying we can only have 3 or 4. It could be, this is the general case. And V1 is going to be dependent on I1. So that expression, that part's going to be JX11 times I1. And then if I'm looking at these impacts of the different currents, then I'm going to have these mutual reactance terms like X12 and X1N, et cetera, that are going to help me define what this voltage drop is going to be across conductor number 1. And what I'm really after right now is I'm after these equations that give me these self-reactances and mutual reactances. And it turns out for the self-reactance, This is 2 times 10 to the minus 7 times omega times the natural log of 1 over the GMR for the first conductor. And then these mutual terms are going to be 2 times 10 to the minus 7 times omega times the natural log of 1 over the distance between the conductor pairs. Note I don't have any resistance in here just yet. We're going to add that in later, the wire resistance. We're just kind of focusing on the reactances for now. All right. So note these mutual terms. What's important here, note these mutual terms are going to be functions of spacing between the wires. And again, the thing I got to take into account is that it's related to the natural log. All right. Now, if I'm talking about like a common sort of a utility system, we could have a 3-wire system or we can have a 4-wire system. Let's start with a 3-wire overhead system. And this is going to be set up for 60 hertz. And so this would be 377 radians per second. If we have a 3-wire overhead, this means we don't have any neutral. What you're going to have is you're going to have a voltage drop that you want to calculate between the sending end and the receiving end. And the load is going to be such for a 3-wire system that it could be, say, like connected in like a Y configuration. And note you don't have any neutral return. So what this means is that this current IA plus IB plus IC, that has to sum up equal to 0. Now I'm going to go ahead and add wire resistances in here. You're going to have RA, RB, and RC. And if I'm writing a set of equations now, they're going to define these 3 voltage drops across these 3 conductors. Then, for example, for conductor A, the voltage drop is going to be the resistance on conductor A plus JXAA, which is the self-reactance term, this quantity times IA, plus JXIB times IB plus JXAC times IC. And you see you've got similar expressions for the B and the C phase. Now, if I would take these formulas here and I would substitute in for 377 radians per second, and if I do a conversion between meters and miles, then what I get is these very famous equations for calculating X, both the self-impedance term and the mutual impedance term. Okay, so XII is 0.1213 times the natural log of 1 over the GMR. This is in ohms per mile now. And then Xij is 0.1213 times the natural log of 1 over Dij, where this is for the off-diagonal terms, all right? So again, this is all functions of spacing. And then if I have the wire resistance in terms of ohms per mile, then I could add that in for wires A, B, and C, all right? So this is probably the simplest sort of configuration we could have. However, a lot of times if we're talking about utility systems, we don't have 3 wires. We would actually have 4 wires. We call it 4-wire types of systems. Actually a little bit more complicated than this because a lot of times we want to have a ground return path, all right? So how do we handle the ground return path? Note that if we have a grounded wire, that not only do you have a current flowing through the neutral, but you'd have to have current flowing through the earth, all right? So what we need is we need a way of modeling the earth return. And if we had everything perfectly balanced, we wouldn't have any earth return. There'd be no neutral flow. However, we just talked about the fact before that these distribution systems are imbalanced. So we need a way of calculating the impact of the earth, and we would need this for fault analysis anyway. So let's suppose I had a wire, and that wire had a resistance, and it had a self-reactance. And let's suppose I just took this one wire, I hook it up to a load at the end, I hook it up to the source at the beginning, and both sides I interconnect to the earth through some grounding stakes, let's say, all right? Well, how do I model the impact of this earth? It actually wasn't a power person who figured this out. It was actually a communications person by the name of John Carson. And so he wrote this paper back in 1926 where the application was in communications, and the power people adapted it toward power systems. And basically, what this paper talked about was an approximation for modeling the effect of Earth. We assume that Earth is basically this big flat plate that's underneath a power line. So you're kind of assuming it's like an infinite uniform solid plate that has a constant resistivity. Now there's other more complicated ground models of this, but this is the one that typically gets used for distribution analysis. And so what Carson said was that, well, if I've got this scenario, if I want to model the Earth, what I could do is I can model Earth as if it were like a conductor that's a distance dE prime from the overhead conductor that has kind of an equivalent, think about it in terms of a GMR type of number that's given by D sub E. In other words, you can think about it as like a dirt conductor, right? You got a dirt conductor underneath the ground. And it turns out that the impact of this dirt conductor is to add a resistance that's given by omega times mu naught over 8, which in ohms per mile is 0.0953 ohms per mile. Okay, so Earth return adds a resistance. And then it turns out there's a relationship between dE and dE primed, where you have this other term called D sub E, where D sub E is going to be 2160 times the square root of the soil resistivity in ohm meters divided by the frequency in hertz, which is normally 60 hertz. And what you can do with this now is you can now calculate a voltage drop across the conductor above Earth and the impact of the Earth. This is going to be our net voltage drop in the system, where this net voltage drop is going to be related to the current IA by RA of the overhead conductor plus this dirt earth resistance of 0.0953 plus J 0.123 times the natural log of D sub E over GMRA. So what's interesting in this case here, it's not really related to the actual distance, but it's related to this soil resistivity, and it's related to frequency. So anyway, this is what's referred to as Carson's equations. This gives you the impact of the Earth return. Now, once you've got this Carson's equation correction, then what you could do is now you can go back to the way our systems are actually constructed. And the way systems are actually constructed is kind of like this 3-wire system we had before. However, when we get to this side, we're going to have a return that's going to return current through a neutral conductor. So this is the 4th wire. This is normally denoted by N. And then we're going to have the impact of Earth, which I'm showing as a conductor here. But actually what that is this Earth here that we're going to model through this equivalent dirt conductor equivalent. So now what I've got, if you talk about all these different voltage drops going across each of these conductors in this model, now you've actually got 5 conductors actually, because Earth's included as a conductor. And you have 5 different voltage drops you can calculate, and they're all going to be coupled together. They're all a function of these 5 currents. And so for the self impedance, you'll be modeling the resistance of each conductor. And then what you're going to have is you're going to have self-reactances on the diagonal, and then you're going to have mutual reactances on the off diagonal, which we're basically, in this case, you're going to have terms like XAB relating AB, IB to the drop across the conductor A, all the way down to the impact of IN and IE. All right. So keep in mind that this current that's actually flowing through this load neutral is going to split between the neutral conductor up on the wire and the Earth return. Okay, it's actually going to split. Part of it's going to flow through Earth, part of it's going to flow through the neutral wire. One thing we're going to be assuming in here when we do this calculation for overhead for our models at least, and this is very common, is that we're going to assume that when we get to these endpoints, that we have an ideal grounding connection to Earth, right? So normally we are going to drive stakes into the ground. Normally there'd be a little bit of resistance in here, but we're going to ignore that. We're going to assume that this is kind of an ideal connection here, and that's going to simplify our math. And so how do we simplify this? Because we don't really want to work with 5 equations and 5 unknowns. That it's going to be kind of complicated to solve. So we're going to go through some simplifying steps for our model. The first thing is we're going to make use of the fact that if we look at this current IE, that's going to be a function of the other 4 currents. If we do Kirchhoff's current law, IE is going to be minus IA, minus IB, minus IC, minus IN. And what I can do is I could take this expression for IE, I could substitute back in here, I can eliminate IE. And then once I've done that, what I can also do is I subtract off equations 1, 2, 3, and 4. I could subtract off equation 5 from these first 2 equations, 1 through 4. And so if I subtract off equation 5, then what I'm going to get, for example, for the first equation, is I'm going to get a modified equation 1. This is going to be VAA prime minus VEE prime, which is going to turn out to be ZAA prime times IA plus ZAB prime times IB plus ZAC prime times IC plus ZAN prime times IN. This is a 4x4 matrix relationship. And so what I can start off by doing is by eliminating that earth pipe in my model. Get this down to a 4x4 system right here. Note that I'm putting a primed in here because this isn't the final number I want to use for like power flow analysis. This is kind of an intermediate step. It turns out when you make this substitution, if you go through the math on this, and this is covered in the notes I'm going to post, that this is self-diagonal term, the ZII prime term, is going to be the actual resistance of the I conductor plus the earth effect plus JXII plus J plus XEE minus XIE. And if you substitute in for these log terms, what you end up with is that this self impedance type of term with the prime on it is the actual conductor resistance plus the earth resistance plus J.1213 times the natural log of DE over GMR for conductor I, all right? And this is going to be in terms of ohms per mile. So this is a modified expression that takes into account the earth return, takes into account Carson's corrections, all right? So this is one term that you're going to need. This is the diagonal term. And the off-diagonal term, this ZIJ primed, is going to be the earth resistance plus J times these terms added together, where if you substitute in terms of the log terms, it gives us J.0953 plus J.123 times the natural log of DE over DIJ. So as far as what you need to know from all this, you don't need to know the whole derivation, but what you need to know is that in coming up with the line impedance model, that this is going to be the diagonal term before we reduce out the neutral wire. And this is going to be the off diagonal term. All right, those are the 2 famous equations that you kind of use over and over again. Okay, now we have 4x4. And that's going to be a little bit more complicated than what we went to do in our analysis. And so what we're going to do is we're going to assume that this difference in voltages is equal to 0. In other words, if I can ignore the ground tie resistance and assume the grounding's perfect at either end, that those voltages across the neutral wire and the earth equivalent pipe or equivalent conductor, the difference in those 2 voltages is going to be equal to 0. So what this means, if you go back up to here, if this term right here is 0, what you can do is you can solve for IN. You could substitute back in here, and you can eliminate IN as a variable. So IN is going to be this 1 over ZNN prime term minus these different voltage drops. And if you make that substitution, then we actually get a 3-by-3 relationship. Now, it turns out that when you make that substitution, then what you're going to end up with in this case is you're going to end up with an expression now for this voltage drop that includes the drop due to the earth return. And this is going to be equal to this particular expression here in terms of IA, IB, and IC. And you'll note now that the ZAA term we're going to use is going to be ZAA prime minus ZAN prime minus ZNA prime divided by ZNN primed, where these expressions right here are obtained by what we sometimes refer to as Crone reduction. Okay, some of you guys might have heard of doing a Crone reduction before. So anyway, what we end up with is we end up now with a 3-by-3. These are the terms now without the primed on them. And what we need to do is we need to take the 4-by-4, and for each of these different terms in here, we need to apply a Crone reduction around the fourth column and the fourth row in the 4-by-4 relationship. So I've got some examples for this where we actually go to do these sort of calculations, but this is what we need to do in order to get the equivalent model, and programs like Windmill actually do all these calculations for you. All right. Now, how does this relate to symmetrical components? Because what I'm showing here is I'm showing a 3-by-3 relationship where, because of the different spacing between conductors AB and AC, these off-diagonal terms are not going to be the same, and the diagonal terms are not necessarily going to be the same either. Okay, so in real life, these off-diagonal terms are going to be different. However, let's suppose the circuit can be transposed. And what I mean by transpose, that every so often down the length of the conductor, what I'm going to do is I'm going to change the positions where conductor A, B, and C are. I'm going to swap them around. That's called transposition, which we use on transmission very frequently. What this is going to do if I swap the positions of phases A, B, and C as shown here, then I'm going to balance out those diagonal terms such as those diagonal terms are all going to have the same magnitude now. So almost like if I take the average of those off diagonal terms, I get ZM. If I take the average of the diagonal terms, I'm going to get ZS. If that's going to be the case, then what I've got is I got the condition that we usually assume for using symmetrical components. And so when you use symmetrical components, that's a transformation between the actual, we call the phase coordinate values, and the symmetrical component values, where we talk about a 0, positive, and negative sequence, where this is given by a transformation matrix. And the transformation matrix is a function of A, where A is going to be a complex number, 1 angle 120 degrees. So if this is the relationship between voltage and current in the phase domain in terms of A, B, and C, I can actually rewrite this in terms of sequence voltages, which we use a lot of times like for protection purposes. And it turns out that if I apply this symmetrical component transformation, that this relationship between sequence voltages and sequence currents is given by this 3-by-3 matrix, where now I've got these just diagonal terms where the relationship between I naught and V naught is given by ZS plus 2ZM. The relationship between V1 and I1, which are the positive sequence values, is given by ZS minus CM. And the relationship between the negative sequence voltage and I2 is given by ZS minus ZM as well. And these terms on the diagonal are the symmetrical component impedances. And so Z1, which we sometimes refer to as the balanced circuit per phase impedance, is ZS minus ZM. It's the same as Z2, where Z0 is going to be ZS plus 2ZM. All right. So this kind of matches up with what you probably saw in a class like 451, if you had 451, where when you got into the symmetrical component values and we were talking about things like Z1 and Z0, that relates to the self and mutual impedance terms as shown right here. And I can actually go back and forth between the two. We typically have a hard time using symmetrical components for distribution because of the imbalance of our circuits. And so if I've got three phase and I'm coming out of the substation, here's my three phases. I have the A phase voltage, the B phase voltage, and the C phase voltage. Yeah, I've got three phase, and if I can assume this is transposed, I could do my calculations in terms of symmetrical components. However, what happens is then we run two phases off in this direction. We just have an A phase and a B phase, and I might run another circuit off that's single phase in this direction. I just have a C phase. Well, how do I use symmetrical components? Because symmetrical components are really designed for three phase. And so later on, we're going to get into some calculations more specifically for fault analysis where we use these phase values exclusively. But I just wanted to point out that even though we can't use symmetrical components directly for a lot of distribution problems, you know, there's a lot of cases where we kind of make use of the fact that, you know, if I've got the symmetrical component values, I can actually go back to the phase coordinate value. So there's some going back and forth we can do, and we'll get into that later on when we do the fault calculations and show, you know, how they're kind of related to each other again. Okay, so let me go ahead and stop here, and I'm going to do some examples. And I know this is kind of complicated, but I think what you're going to see when you actually start applying it, and you just kind of use some of the formula relationships that I showed you, that you don't need to worry about all this complexity. You just have to kind of know how to apply the formulas and then go from these prime impedances to these final impedances. They're doing like the Chrome reduction.